Thanks to the talk of Professor Marcos Oliveira from University of Campinas. The talk is entitled Nonadiabacity and nonclassicality of harmonic oscillators with time-dependent frequencies, exploring the dynamics of trapped ions. Okay, Professor.
Okay, so again, thank you very much for the invitation. And I do know Vitor for quite a long time. Actually, while I was doing my PhD, I was a PhD student with Professor Mishai. And then Salomon invited Vitor to be part of a meeting because he wanted to show some results, or to me to show some results, because I have the impression that I was not getting anywhere. So he wanted the input by Vitor, so perhaps we could get something out. But I think that I was not that quite exciting at the moment, because while I was at the blackboard and I turned away, they were sleeping. So yeah. Yeah, and what you do when you are a student, a PhD student, you don't disturb them. I just waited there for them to wake up, and then we went for a coffee. That was the best option we had. But I have to say that this was very important. We have a sort of quantum optics school at University of São Carlos that started at those moments. And this is quite important in Brazil. So there are many people here that comes from this school of quantum optics. So we do have our own approach. I would say that we have two schools in Brazil. One is the Rio de Janeiro school, and the other one is related to Campinas and São Carlos. So we are, like it's quite significant the amount of work that came out afterwards from people coming from those two places. So I think that it was quite important. The things that I learned both with Salomon and also with Vitor, and I learned a great deal of mathematical methods to deal with problems. And I think this is the best thing that one can get out of his PhD. And we had the chance to get more exciting things in the future. So we had a few papers. One was related to my PhD, and another one afterwards establishing a theory for photo detection that was actually quite important. And those many the papers that we generated from this collaboration, they actually were important to generate, more a great deal of work from the same group. So. Yeah, so thank you, Victor, and congratulations for your birthday. Okay, so for those who doesn't know me, I'm Marcos de Oliveira. I'm the Institute of Physics at Unicamp, and so yeah, and I do work. Let me see. No. It's not working. Oh yeah. Sometimes you have to turn on the. Okay, so I do work with a few things related to quantum technology and foundations. So there are many subjects that you can check afterwards related to the kind of work that I do. Everything here I do understand in a similar way as a quantum optical devices and the theory behind quantum optics. So even though there are many subjects, for me they are all the same. So, but I will talk about something which I started working in a few years ago, and it is related to quantum thermodynamics, or to understanding what is quantum related to this so-called quantum thermodynamics. And we wanted to, what everybody wants to do is to understand how quantum features they affect classical formulations of thermodynamic axioms. Okay, so this is quite pretentious, so I don't want to talk about all of those things, but mainly what we do is to understand how entangled systems involved in thermodynamic process, how do they work, and also coherence. I'm not going to talk about entanglement, I will talk about coherence, and in this fashion is quite similar to what Lucas talked about previously this afternoon. Oh, okay. So in a summary, I will just cover in a brief introduction what is quantum thermodynamics, what we mean by quantum thermodynamics. Afterwards, I will talk about squeezing in non-classicality as resources for quantum heat engines. And I will, at the end, I will talk about nonadiabacity and non-classicality. So this work was publishing back in 2002, and the other one is underway. So we are developing that. Some of those will appear soon in the archive. Okay, so let's go. So what is quantum thermodynamics? So thermodynamics in general doesn't distinguish what is classical, what is quantum in a physical system. So we do know, I'm not going to detail all the laws of thermodynamics, but we do understand that thermodynamics analyze thermodynamic quantities of system composed of many particles. So this is one thing that is quite understood. And the other one is that the thermodynamics is also, at least the first law, is a conservation property of energy. And the other laws are, related to this conservation and how we can distribute interacting with a system specifically by doing work and doing and exchanging heat with the external system. Well, quite sorry for that. Yeah. I don't think there's a way to fix this. Is it? No. Well, doesn't really matter. I will move on. Okay. So if we have, I don't think we have more. We do. Yeah. Sorry for that. Eu tenho acesso à rede? Porque aí eu ponho no Google Drive. Sorry for this. Preciso acessar. O que você mandou por e-mail? Não, eu preciso acessar o que eu mandei por e-mail. Deixa eu ver se não. Faz tempo que você mandou? Eu mandei para ele. Você mandou o PDF mesmo, né? Mandei o PDF. Ele está certinho. Vê aí se tá. Esse aqui. Se não, eu acesso. Esse daqui que você enviou agora? Isso. Deixa eu dar uma olhadinha. Tá, então peraí. Então, não, eu preciso acessar o Google. Entrou nessa conta? É. Então, pode entrar. Já? Mais fácil. Onde que eu entro? Achei para mim que tá. No Gmail, né? Você vai entrar? Isso. Você tem verificação de 2 etapas? Acho que não. Manda mensagem do celular? Não, não necessariamente. I told you I was going to talk for 1 hour and a half. Wow. Eu acho que não é essa senha. Yeah, I think it's better. Is this okay? Oh, can I? Okay, so where is the pointers here? Okay, so, okay, sorry for that. And I hope everything is fine now. Okay, so yeah, so the introduction that I was mentioning about thermodynamics. So let's go here. So quantum thermodynamics deal obviously with quantum systems, and we do know how quantum systems they do evolve. If you have an isolated system, it evolves according to the Schrödinger equations. We have also a way to describe it through the time evolution operator. We describe the system an ensemble of system by the density operator, which due to the unitary evolutions evolves to this future state. So the equation governing that is von Neumann equation, nothing new here, but isolated systems are not that interesting to work with. So we do work with a non-isolated system or open quantum system, where we have a system and a bath described in the Hilbert's joint Hilbert space by the state of the system and bath. So this is quite natural. Everybody here does similar stuff, which is related to a system coupled to a bath. So this is quantum thermodynamics, really, but we don't call it usually quantum thermodynamics. But always when we treat a system which is in contact with the reservoir and we treat how it reaches the equilibrium state, we are dealing actually with thermodynamic processes. So the evolution equation is the von Neumann-Liouville equations, where we have the operators for the effect of the bath over the system. So, okay, so we have to mention a few things related to thermodynamic process before we move on. So the first law of thermodynamics is given by the again, the conservation of energy, where we can calculate the incremental evolution of the energy like that. And we call it, as we saw before by Lucas, that we call it, this part we call it heat, the one which is responsible, and we say that this is uncoherent, even though there are coherence as well in this term. But the one that we know that this is surely coherent action, we call it work. So this is easy to identify. This is not that easy because there are problems in that relation. But the description I'm going to use is that I will use, I will split this evolution of the energy in two parts. One is the heat. So everything that's calculated in that fashion is heat, and the other one, which I call a coherent action, is called a work. Okay, so when we do a thermodynamic adiabatic action or adiabatic process in terms of thermodynamics, when we do this over this quantum system, we are actually by doing some external manipulation, and what we do is just evolving the system through a unitary evolution and calculate the system, the state of the system, the central system, that we call it rho zero here. So then when we calculate, if we have an adiabatic thermodynamic process, we have that the amount of heat is zero, but then the work is easily calculated by this amount. So, okay, so there's no exchange of heat with the system and the reservoir. That's all. We all know this. And when we do an isothermal process, is a little bit different. We do an external manipulation, plus we have a reservoir coupling as well. And the state of the total system is given by that. And we have the total Hamiltonian, which is described by the Hamiltonian of the system that can depend on time, will depend on time for us, because we will be interested in process, evolution process, the Hamiltonian for the bath, and the interaction. So nothing new again. It's all that what everybody knows about open quantum system. But now I move a little bit further and talk about the system that I'm going in, what I will call the the system that I'm going to describe. I need to talk about squeezing and non-classicality. So if we have thermostates, so for example, let's suppose that I have thermostates inside a single mode cavity, and so the quadratures, the variances of the quadratures of these thermal mode states are given by those numbers, and the uncertainty on both quadratures for the thermal state are the same. But there are more interesting states. So this is a thermal one, but there is another one which I need some nonlinear effect to act over the system. So I could have, for example, a single mode squeezed state. And this is well known. It's a minimum uncertainty state where we have that the variances of the quadratures, while depending on the squeezing parameter, which I call R, this one, if I increase R, this guy gets smaller, gets squeezed, that's what we say, and the other one increases, which is in the orthogonal direction. So usually this is performed by acting over the vacuum. This is the situation that generally we have by a squeezing operator. So if we had this thermal state that I just described before here, we would end up with a squeezed thermal state. So this is not a thermal state in the real sense. So we cannot say that this is related to equilibrium with a thermal reservoir. So it's called a non-thermal reservoir because we have this squeezing that affects the system by introducing some coherences in the system in general. This is not usually true when you have a thermal bath. Usually just washes away all the coherence in the system, but a squeezed thermal state, it does give some coherence for the system. Okay, so all right, so why? So I talked about non-classical features, but let's see what is non-classical or classical about those states. So there are many ways to describe a classical state. The best one that I find, and I worked for very long with that, is the description through the Glauber-Sudarshan P distribution. So this every state can be described in terms of this sort of orthogonal decomposition, but only those which are described by legitimate probability distributions here, P of alpha, are classical states. So for example, if you get a coherent state described in terms of the P representation, the P distribution is a delta function, okay? So delta distribution. So this is quite well known. But all the other ones, the distribution must be negative or, be divergent, so which is similar in some way. So all those states where I have a non-legitimate probability distribution, they are non-classical states. So why this is better than if you go, for example, for the Wigner distribution. The Wigner distribution, for example, if you calculate the Wigner distribution for the squeezed state, it's non-negative. So usually people address to non-classicality in terms of the Wigner distribution as being a negative distribution. So that doesn't work for squeezed states. I mean, it's a classification. But everything that is classical in terms of the P distribution for sure is classical in any other senses. Okay? So let's see how this works when we have specific states. So why I do like this P distribution. So let's suppose that we have two sources, one of classical states and the other one for non-classical states. And we mix this source with the vacuum in a beam splitter, a 50-50 beam splitter. So whenever I have classical states in this input, so this is a theorem actually, I will have a separable state at the end, right? But if I do get a non-classical state in the sense of the P distribution, when we mix it with the vacuum in the beam splitter, we do get a non-separable state or an entangled state. So in that fashion, the P representability can be transformed in a measure in terms of a resource for entanglement or not. So this is what. So if it's a classical state, doesn't generate entanglement. If it's non-classical, it does generate entanglement. So this is quite important because this is a theorem. It works for every single situation. Of course, we don't need a beam splitter. We need a beam splitter operation over your system depending on how the bosonic modes are described in the system. All right. So summing up what I talked about, squeezing is a quantum effect rooted in Heisenberg uncertainty principle. Squeezed states encompass states with non-zero coherence in the energy eigenbasis. P representability can be used as a tool to discriminate non-classical states. So now I move on to the parameterization that I need, like to describe it. We go to a symplectic description because usually we don't work in the Hilbert space. So usually when we are talking about bosonic modes, we have an infinite dimensional Hilbert space. So it's better to move on to the phase space where we have a description in terms of a symplectic structure. So for example, when we describe a single mode, well, this is our work substance with a single bosonic mode. So it will be described by a covariance matrix. And this is quite important. We do understand lots of things, actually everything that is related to the system, if it's a Gaussian system. If it's not Gaussian, we do know some things about a few things about the system. And we do know, for example, that in terms of the P representability, classicality characteristic, we know that this classical whenever the average number of photons here, or bosons, is larger than this out of the diagonal quantity, which I call M here, all right? So following this description, it's possible to define what is called a classicality function by just, defining the difference between those. So whenever this guy is negative, this will give me a non-classical state. Okay, so I'm just using these parameters to quantify. So for example, when we have the thermal, remember that I mentioned the thermal state, and when I do have the thermal squeezed state. So when you calculate the thermal squeezed state, so depending on the squeezing, if I had the squeezed vacuum, this is quantum whenever R is different from 0. But when I have thermal squeezed states, there will be a competition between the temperature, the description of the temperature, and the squeezing parameter. So it's not always that this state is a non-classical state. So I plot it here in this parameter. So I just vary the squeezing parameter for a fixed temperature. So for each value n here and for m, I have a space which characterizes all possible changes. So in this blue area, I have all the classical states. That means that the temperature is so high in that situation and the squeezing is so low that I do have a classical state. And if I move on, I increase the squeezing parameter, then I do have a non-classical state. So that's, and then we have this non-classical area here, and we know how to calculate the critical regime for the squeezing, which is given by this number here. Okay, so of course it depends on the temperatures. So for different temperatures, we do have some curves for this classicality function in relation to the R. But keep in mind this, because this we're gonna use for expressing our thermal heat engine. So take-home message, it's possible to discriminate a non-classical state by the sign of the classicality function. So just for you to know, everything that is below this horizontal line is a non-classical state, and everything that's above this line is a classical state. All right, so how non-classicality affects thermodynamic quantities. So now we move on to the first part of results that I wanted to show. So let's think about the system. So the problem is I have a quantum heat engine which is made of a photon gas. So I have a single bosonic mode which is coupled to two reservoirs. One, it is a temperature which I call cold, and the other one a hot reservoir. which is a temperature, a higher temperature. But this hot reservoir also has some property. It is a squeezed thermal, is prepared in a squeezed thermal state. So when we do this cycle, meaning that we first put in contact with the cold reservoir, we squeeze the system, then it is described by this oval shape, and then we put it in contact with the squeezed thermal reservoir, and afterward we squeeze it in the orthogonal direction and so on, finishing with the cycle. We are able to generate a cycle where we use this coherence in terms of non-classicality as our working substance. So this is the idea. So there are two possible cycles here. One that I vary the classicality of the system through all the cycle, and the other one where I keep it constant all the time. All right. So I'm not to describe this in more detail because I want to talk about something else. All right. So how we describe this, it's easy. It's similar to what I described just before. I consider I have a bosonic mode and a bath of bosonic modes. And then we evolve this and consider all the equilibrium states for this system. So, all right. So when we perform this cycle, we can have, for example, an Otto cycle, which is this one. And we have two isentropic processes and two isochoric processes, and the squeezing parameter is modulated in this situation. So this is the cycle. So we are using the classicality, to perform our cycle here. And more importantly, in the situation, we have that the efficiency of these guys is the guy can reach a number close to 1 depending on the squeezing parameter. So this is not new. Some people also knew this. This is not the only paper that consider non-classicality in terms of the squeezing and consider a thermal heat engine as with the squeezing. There are many papers out there, but depending on the classification, you have different results, and we use the non-classicality as our working substance. So just for you to know, there is no Carnot cycle here in the situation, but if we had, because it's impossible here to have distinguished adiabatic curves crossing two isothermal. They are both the same in this situation. But if we had the efficiency would be around here, meaning that when we squeeze the system and we have a more non-classical features in the system, so we have a better efficiency. So that's all. So that's the idea here. We can also have a generalized cycle where we allow the squeezing parameters to vary, but we keep the classicality function to stay constant. How we can do that? Of course, when we squeeze it more, we have to increase the temperature as well in a way to keep the classicality constant. So that's the idea. So in here, so we have this different cycle here. And I'm not going to describe in detail what we have here, but the important message is that we have three regions here which are important. I have one first region where I have this efficiency here, which is below the supposed Carnot heat engine efficiency. And this is the situation where I have a classical, I start with a cold classical state, and I go to a hot, sorry, just a minute. Where I start with a cold thermal bath, and I end up with the temperature of a classical and hot thermal bath. The other situation, I start with a cold thermal, a classical reservoir, and finish with the situation in the cycle with a quantum reservoir. And the third area here is the situation where I start with both a non-classical thermal reservoir in the cold reservoir and a hot reservoir here. So we see that if we have this machine working, this engine working in this region, or even in this region, which is above the Carnot regime situation, we have a better efficiency than we would have in the situation where we have a classical heat engine. So why is that? Because we are using coherence. Coherence in the system somehow helps, to extract more work of the system out of the system. Right. So to describe these results, I cheated on you because I gave you just stable solutions for this evolution. We understand that when we have two thermal baths in contact and we change the temperature between them, we know that this temperature, the system will take some time, to reach the equilibrium with the thermal reservoir. But we are assuming that this is made of an infinite number of reservoirs that I put in contact in a way that I described the evolution, and the system is always in a quasi-static and equilibrium state, right? But I didn't mention this to you. I'm just giving you the initial reservoir and the final reservoir. So to describe this in a dynamical way, I must go to a dynamical description, but then we have a problem. The system is not in equilibrium with the reservoirs all the time. So that means that we have to describe a non-equilibrium system in contact with these reservoirs. So in thermodynamics, there is an area which is called stochastic thermodynamics that describes just this kind of situation. And in this, we are going to apply specifically this situation, but I'm not going to, but when we have, when we are dealing to time-dependent system, we have a problem that I will show you in the second part. So how can we implement it? So I mentioned this optical field, so we could do this in principle, but this is harder to manipulate. So there is another way which is nicer to do this, which is by using ion traps. So ion traps, they are quite important. So we have here represented many pole traps, linear pole trap and also planar pole traps, and where I have like a saddle potential here. So when we put, for example, this ball here in the saddle potential, and this potential is spinning, so the ball doesn't know where to go. So it always is in an equilibrium state there. So this is similar with this quadrupolar potential here. So if I have an ion here and this quadrupolar potential is, changing the polarities in a way that the ion doesn't know where to go and it keeps in a stable position. We can approach, so this is actually what is done in quantum computers based on ions. So this is a planar quasi-potential. So this is the figure of what we have. So when we consider that we are, in the harmonic approximation situation where we are near the center of the trap, what we have is a harmonic potential, and we know all the states that the particle, the vibrational degree of these ions, they could, occupy one of those states. Those states, of course, are quantized in this situation. So, okay, so there's one important thing. So people know that when I get this trap, for example, and I modulate it with time, so I have two situations here when I have a sharper trap and a trap with its brother. I do change the frequency of this, the transition, the possible transition of this trap. So this is quite useful for generating squeezing. So there are the first paper that I know of, quite possibly there are older papers, but the paper that used this strong squeezing by repeated frequency jumps was back in 1992 by Jansky and Adam. So it was published in PRA. So here I have a normal coherent state. So this state is evolved to a squeezed state. I wait for some time for the state because I have the free evolution, the state, the phase of the state is evolving. But if I am right at the correct, time, I actually can squeeze it more and more and more. So this is quite important. So, but this, what was proposed, we have sudden changes, which usually doesn't describe, they don't describe what we have in the lab in the normal situation. There's another paper back in 2009 by Eric Lutz and Galv that gave this situation, and again, a strong squeezing, but, using this situation where we wait some time for the state to evolve as well, and we keep squeezing all the time. If we don't match the phase, the free phase with the evolution of the system, what we do is squeeze and squeeze in the orthogonal direction in a way that I would have the coherent state back at the end of the day. Okay, so I have a reversible way to do that. But question is, I have two limits where these were considered, and I don't want to go to those limits. I have the situation where we can do the adiabatic approximation, where the frequency is manipulated slowly, adiabatic here in terms of the dynamic, of course, and there are no transitions between the different energy levels. And here it's not possible, it's known, that it's not possible to generate squeezing effects. Also, this is related, if I want to use it for thermodynamics, this would correspond to thermodynamic quasi-static process. So this is this situation. The other one, which I just showed to you, is the sudden approximation, when the frequency is manipulated in a very short time interval, transitions between different energy levels, they do exist, and this exhibits a higher degree of squeezing as they proposed. All right, and in this case, we do have the correspondence of a thermodynamic irreversible process, but we don't want to use neither of those approximations. We want to go, to have an actual and general result. So this is actually interesting because back in 2001, there was one paper which is, an experimental-based paper here that just showed this, how can you do squeezing in the motional degrees of freedom of the ion. And in 2001, also by this group in here, it was shown as well the similar way, just by modulating the trap. So we are thinking about the system because this is a very controllable system that we can use. All right, so how can we treat that? We have a parametric harmonic oscillator, and I will consider that the frequency is time dependent, and I do have my position and momentum of this ion here for the vibrational degree, but I can also go to another reference frame where I do have different operators, B and B dagger, which are related to this guy, but I do have explicit the frequency as described here. So either I do have this, or I could have this Hamiltonian here with the frequency described in this way. So this is quite important. I have two different definitions for the annihilation and creation operator when we have to move forth and back from both references to be complete. So this solution of this evolution operator B and B dagger are given by this relation here, which are related to the squeezing parameter, which is I call here RA. And we can get this by the squeezing transformation correctly in the same fashion that I just showed to you. So what is the squeezing parameter? The squeezing parameter is related to the rate of the time-dependent frequency and the original, the one frequency that I start my system off. Okay, so I scale it with that. So after that manipulation, we end up with a nonlinear Hamiltonian, which of course introduces squeezing as I just mentioned to you. But have notice that I do have this parameter here already, which is related to, and I have the variation of the time here, but I also have, some time, some parameter that will introduce another kind of squeezing as well. So we have two squeezings in this description. At the end of the day, when we describe the dynamics correctly. And okay, so we can describe this by the equations of motion. Just assume omega as omega of dependent of time. We have the possible solutions, It's a little bit, cumbersome, but it's not difficult to do that. And we end up with the results by using some Lie algebra, and which are related to some important parameters that I just described here for you. So why those parameters are important? Because then afterwards, if I average the Hamiltonian, if I average my Lagrangian and this coefficient here, I end up with those three parameters which are related to the so-called adiabatic quantity or non-adiabatic. So this definition here was used by Husimi himself back in 1953, to describe a non-adiabatic process. So we have a diabatic in the dynamical sense whenever this Q prime is 1, but if it's larger than 1, we have a non-adiabatic process, all right? So let's see how it works. So after working with my details and with my covariance matrix, so we identify this average of those three quantities that appeared in my Lie algebra, and I do have the classicality function written in terms of this non-adiabaticity quantity. So of course, there will be, remember that to have a non-classical state, this quantity must be negative. So there will be, depending on the temperature, there will be a non-adiabaticity quantity, that a critical non-adiabaticity quantity that will give a negative number here. All right, so this is the important thing. So we related the non-classicality with this non-adiabaticity, and this has some nice, important feature that I will just show you. All right, so just by working here and plotting for some specific temperatures working for ions, what we have here is that, like we have the critical non-adiabatic parameter, and what we see here is that the system, to be non-adiabaticity is not sufficient, not a necessary condition to have a non-classical state. But for sure, if you have a non-classical state, then this state is also the process, the dynamics of the system is non-adiabatic as well, right? Okay, so let's move on. To consider the system in a proper fashion, I have to solve in a different way. I have to use a time evolution operator, and this is quite important. Believe me, I don't want to, to move on in the details of the paper. So we have this different description in terms of this evolution operator, where we have the conditions to be satisfied, and we use it for the evolution operator and ansatz, which is described by the product of a squeezing operator and rotation, which are just described here. So we have this new squeezing parameter. So this is a different way. And by fitting those phases, we have a correspondence with the other model, the other way that I just showed to you. But this is important because we recover those quantities that I had here. And again, I have a similar squeezing, similar to the one that I just described to you. All right, so why I use this treatment? Because this treatment, I can use this to describe what is, stable or non-stable in this situation. So, of course, I will use some conditions. So the temperature is given by that quantity here. I use initial thermostat. But I do consider that my frequency follows some standard experimental parameters and is given by that quantity here. So when we put that back into the equations of motion that we had for the situation of the time of the evolution operator, what we end up is a Mathieu equation. All right, so this we know how to solve. This is important. And the Mathieu equation will give us two different kind of solutions. The ones which are in the white area are stable solutions, meaning that the solution doesn't explode, and the other one are unstable solutions. We have quasi-periodic orbitals here in the borderline, but we are not talking about that. So we fix our parameters in that situation. So remember that my frequency is written like that, all right? And when we do that, what we end up is with two situations. One for the stable situation, and notice that my non-adiabatic parameter is very close to 1, varying in the in this third case. I mean, it's very close to 1. Yeah. And so even though I changed the parameters, of course, taking this situation for them to be really close, to the region, to in the stable region, what I have is a adiabatic process here. So all those curves, they are comparing the situation when I solve it to the through the time evolution operator, and when I solve in the first situation where I use the Heisenberg equation. All right. So there are some situations where we know that when the one approach is should recover the other one, which is usually when we go from here from multiple of pi in terms of the time parameter here. All right, but this is not the most important result. The most important result is this one here. When we are working the stable solution, what we have, even though if it's non-adiabatic, so we see here that this guy goes well above the number 1, so it's non-adiabatic evolution. But what we have is the stable solutions which recover with time. All right, even though if the period can be different from, depending in which part of the area we are. But of course, we also can compare the non-classicality compared to those parameters, and we see that there are regions that we can have classical, non-classical states, the red ones, and classical states, which are the blue ones. All right. So classical states are those states that we don't want to use them to extract more work from thermal heat, from heat engines, and so we want to work in that region. But if I go to the unstable region, then we have something else. So so you can see that the non-adiabatic parameter it explodes with time. So it's very large compared to the critical value of 1. And I also see that my non-classicality, it goes really fastly, goes below below 0, which is important to have non-classical states, as you remember. And we also have some features here that it doesn't matter. What is important here that we always, when we work in that region, of course, we have a critical, when we go above a certain critical time where the squeezing affects the system. So whenever we have in this area, we will have non-classical states, which are states which are important for many things. One of those things is to extract more, we are able to extract more work from the system. Okay, so conclusions and outlook. Firstly, classicality, a simple but with a good predictive power. Second one, the non-classicality is a resource for quantum heat engines. Of course, you could go, like I think that Roberto is going to talk about coherence in general way for quantum thermodynamics. So this is a similar result, but speaking specifically about non-classicality. And the other one is that the relationship between non-adiabatic dynamics and the non-classicality of the parametric oscillator is described by the classicality function, which is nice. And the fourth one is that the existence of a critical value of the non-adiabacity parameter shows that a non-adiabatic manipulation does not necessarily generate a non-classical behavior, while non-classicality defines a non-adiabatic dynamics of the oscillator for sure. All right. So with that, I thank you, and please have a look at those papers if you want. The other one, it's not in the archive yet, but will be in near future. Thank you very much, and congratulations, Vitor.